You don't have to make an appointment, but you can make an appointment. And you can drop an email and you say, you know, tomorrow I want to come, and I don't know. And then they know a bit on the low. Then basically what you will get a platform which will be related to what you heard yesterday. Because yesterday you had a surprise, you didn't see me. Are you homesick of me already? Or were you homesick of me? I don't think so. And then we'll give you a platform with the Rovex, or built around Rovex, and you will have to do some kind of architectural optimizations. At the end of the lab, you have to submit a report with your findings and your comments on the findings. Then you have to, then it is a bit independent work in the sense that we give you freedom, but not full freedom. Then we don't let you fly or drive, swim without any kind of support. Now, depending on how the report will look, you may also have to talk with the team which is running the lab, which is essentially my colleague, Stefan Wong, and the two PhD students. Actually, one is PhD student and the other one is a postdoc. I may also get involved, but I'm not sure about that. You will have to talk with me in relation with the other one, with the reading assignment. For sure, that will be the case. Then, my first request to you is try not to come that late in the lectures. And the second one will be to form groups and to email me the composition of the groups. When you do that email, please name, study number, and email. Okay? Because I have to do my own administration to keep things under control, and if you don't provide me enough information, you make my life more complicated. Okay? Then you can cluster, prepare group in the way you like and please. If you do not have a group, eventually, just let me know and I will try to do some kind of matching. Okay? I'm not a dating agency, but I'm going to try to cluster you somehow. Now, what will happen is that we will still have some classes next week and probably the week after that, one or two, most likely two. And then after that, you will be in the evaluation part. Then you will be getting the reading assignment and the lab assignment, and you will work on them on your own tempo, but there is a condition. You have to deliver the goods at the end of October. I think the deadline for the reading assignment I put on 27th of October, and we should be doing the same for the lab. We may play a bit more flexible, but for now, this is the target. After you deliver those, we'll start evaluating them, and for the reading assignment, I will have to speak with each and every group, probably around 20 minutes to half an hour, in which you have to convince me that you did a good work, and you also have to convince me that all the members of the group contributed. Because if you just submitted me the report and 3 authors, how do I know that all of you did contribute? Then I would like to have a friendly chat. Now, during the friendly chat, I might have the weird idea to ask you about some computer architecture phenomena. Then it will be like an exam, an oral exam about computer architecture in general, with the focus on the topic that you are choosing. Then careful, this is a dangerous exam. It's not like one where you have questions and it's clear. No? Then the discussion can develop in unexpected ways. Okay? My goal is not to fail you. My goal is to pass you. But you have to help me. Okay. Now, For the lab, we are preparing now all the things, and most likely we will release the package on Blackboard, probably somewhere around maybe 2nd, 3rd October. I'll let you know next week more. Then when you get the package, you can do things further with no problem. Now for the reading assignment, I will give you complete freedom, which means you may choose for reading assignment whatever topic you want, which is relevant for computer architecture. Let us assume I want to speak about emerging technology memory systems. This I can see from very many angles. I will not care if you will tell me, let's say, about the physics of memristors, about the device level or the circuit level. If you choose such a topic, you have to look at it from the angle of the computer architecture. Then you are free to choose whatever is relevant to computer architecture, focusing on the work which is at the computer architecture level. Because, you know, I can build logic with spin devices. And I can take, instead of MOS transistor, I can take some kind of spin devices, and I can build logic. This is logic design, it's not computer architecture. If I choose, let's say, spintronic architectures, I should look at the spintronic from the point of view of the architect. Then how are things done there at the higher level? Now, you may choose things which I just mentioned, which are exotic and very, you know, attractive. But you have to be sure that you are doing the game at the level which relates to architecture, not to circuit, not to device, not to technology. You can also choose things which are from traditional architecture. Let's say I choose to deal with branch prediction. Okay? And if I choose branch prediction, what I will do, I go in IEEE Explore. In IEEE Explore, I will select 3 to 5 publications which are dealing with branch prediction. Now, what I want is to have 3 to 5 publications which are dealing with branch prediction from different angles, not incremental work in the same direction. Because, you know, I can propose something, then you can come slightly later and make a baby step and another baby step. Things are going like that in research. But also we have big avenues. Then, if you want to have a good reading assignment, this is a very fundamental point, the starting point. Choose the topic and choose the papers that you want to discuss. Now, assuming that I did branch prediction and I made the choice from IEEE Explore, you all know what IEEE Explore is, right? No? Just Google it. Nice. And you can Google it whenever you have an IP from TUDEL. Because otherwise you Google it, you see it, but you can't get the information from there. It's a huge database with all the publications which are sponsored by IEEE, conferences, journals. Then I went there, I got my candidates. Now we are in a group, we split somehow the work. We read the papers, and it would be advisable that we all read them. And then we start discussing. And the point of the discussion is to generate a nice report. In order to generate a nice report, you have to understand what the approach in the paper is, in each of them. Where are the essentials? What is good and what is bad about each of the solutions? Then, in your report, after understanding that, you have to present the problem. you say, I selected that. You have to say, why is this important? It's relevant, whatever, and then you start presenting the 3 or 5 kind of avenues. You should not copy from the papers, right? Because I can read the papers. Not that I have the time or I'm interested to read them all, but if I want to, I can read the papers what I want to read. I want to read your opinion. Then in your one words, you have to write down what's important and what is specific about each approach. Make a pros and cons analysis, and eventually conclude with your view on the issue. Let's say this is what other people did, and I see what's good, I see what's bad. I would have loved to go in this direction. Okay? Then you may or may not be able to make such a proposal. Now, let me put it in this way. If you have a good analysis, it's certainly enough to pass. If you want a 10, you have to be creative. Then if you convince me that you got, let's say, the fundamentals of the problem, and you can come with a proposal which potentially can be interesting, I will give you a 10. It won't hurt me. Actually, it will do me pleasure. Then, basically, that's the story of the report. Now, a report should be a decent report. I saw many reports in my life, and most of them are not really well organized. And I assume that at your level, it's not your first report. And from now on, you will have to write a lot of reports. Then you have to learn how to do it in a proper way, okay? Then, with a decent structure, organization, you have to follow a red wire in the presentation, you know, Ariadna. The Ariadna in the maze, you have to do the same as Ariadna. Okay? If you don't know Ariadna, you should Google it. Then, if there is a red wire in the discussion, it is clear to me that you judge the things in a proper way. Then, give attention to the way you write. Try not to make that many grammatical errors. You have tools which are helping you. Okay? In all those aspects, you are tired, sir, or this discussion is boring. So I'm just trying to help you to do a good job. Then all those aspects will be evaluated in the discussion, you know. Quite sure the show, when we meet, that part is also important, you know. There is a certain radiation that people are sending whenever they are sure about the domain and whenever they are not really, you know, in you could not see my email anyway because the dog is watching. Then, are we clear? Yes.
So the 5 applications should be 5 different avenues, not 3 different avenues and then 2 or...
Now, depends on the domain. You may be able to find 5 essential different avenues or not. What I would not like to see is one method, only and incremental things on that method. This is something which I would not like to see. Now, in order to do some damage control, I would like you to send me the topic and the publications that you want to scan as early as possible. Now, let us say we started today the discussion, you start clustering. Whenever you have a group, you can think about a topic. you decide about the topic, and probably not next week because I don't want to stress you too much, but the week after that, let's say Tuesday, it's a good day. Yeah? You send me an email with the group and the topic. Now, you don't have to wait until Tuesday. If you have the group and the topic tomorrow and the papers tomorrow, it's also good, even this evening. No problem. But I would like to be sure that everybody is part of a group. You have a topic which I consider reasonable, and you have some papers which are okay. Now, probably now you are not that many in the room, but I think there are more people which are taking this class. I will not explain that once again. It's their problem. I'll put some information on Blackboard, but this show will not happen again. Okay? Then, according to our kind of calculation, around 60 students are taking the class, which means I'll have to deal with 20 groups. Then it's 20 versus 1, actually 60 versus 1. I'll manage. Now, if you put me in, under pressure, then I may have a bit of delayed reaction. Yeah? If all of you will send on Thursday or on Tuesday, so it's a good day, then it will take me some time to screen them. But basically, you can assume that from now, you can start looking for partners, make a group, look for the topic, computer architecture topic, and can be, you know, can be caches, can be branch prediction, I don't know, instruction, speculation, renaming, you name it. VLIW, as you heard last time, then you can also deal with emerging things. You can go on quantum architectures. I will not have a problem with that, as long as you can tell me something about quantum architecture from the computation point of view. Not about putting Toffoli gates one after the other and doing some kind of excitation of the quantum fabric. Okay? I'm talking a kind of different language now. But that might be the future of computing. It's slightly a bit too early for looking in that, but it's attractive, it's interesting. Do you have questions? Once, twice? No questions? Yes, sir.
How many papers should be
Sorry?
how many papers should be reviewed?
Didn't I say that?
3 to 4?
3 to 5. 5 is better because you can even do 6 to the person. Because 3 might be too few. Depends on the topic. If you find 3 papers which are representative for the topic and which deal with the topic in very different ways, then it's okay. I don't want to impose too many things on you. I like freedom, then I like to give freedom. But freedom is dangerous and most of the people don't like it because it comes as a package with something else, you know, which is called responsibility. Then it's better to be pampered, you know, than to take responsibility. But this is not the way we do as grown-ups. And you are grown-ups, to me. Is that a wrong assumption? No. No, because if I say you are kids, you would be jumping here and protesting, right? Then you are grown-ups. Yes.
Sorry, 3 people for the groups is for both as reading assignment and
You
both?
can change the group if you want.
But I mean, tuning is enough.
Green the group will be for both of them.
Both of them. Okay.
For lab and for reading assignment, and it will be better for you if you stick with the same group.
Yeah.
Now, be careful when you make the group. I really hate to do mediations. It happened to me in the past that people were coming and were saying, you know, I'm the only one working. The other ones are not doing anything. Or things like that, I don't want to hear. Actually, if you have a problem, for sure you have to come forward. But somehow, when you choose the group, try to make it in such a way that there is chemistry with the other people, in the sense that you can work together, you collaborate in a proper way, and you have the same goal. Okay? Because if I target a 6, and my colleagues in the group are targeting a 10, why would I work for a 10? I don't want a 10, 6, it's enough for me. Life is all about priorities. I'm not really fan of the American culture, but this is something which I like from what they claim. Why am I not fan of the American culture? Because I'm in Europe. Okay. More questions. Brilliant questions. Gold questions. What is your phone is not saying anything? No? Okay. I saw you are very busy with it. Do you remember what I said?
Yeah.
Not you, the one. Yeah? Okay, brilliant. Then, if there are no questions, we return to our material. I just have to do something to get some light on the... Then, I assume you are happy with the setup? You cannot complain anyway, because those are the rules and regulations. You know that each part will come as part of your work. Now, from my point of view, I would like you to finish both parts in the same year. But it happened in the past that people completed only partially the class. I would love not to have such a situation, at least not this year, because next year this course will not be given any longer, or not in this way. Then next year we'll change again curriculum. You know, there is, in order to get to the optimum structure, you have to keep on looking around. Annealing. Do you know what annealing is? From metals. When you treat the metals, you go to high temperature, it's a lot of kind of movements due to thermal vibrations, and eventually the structure will crystallize in a proper way. This is happening in many other systems. Then try to complete both of them this year in order to avoid headaches for yourself and for myself. If you don't care for me, just care for you. Okay? Now, yesterday my colleague came and he told you about the LIW course in general and about the core that we developed in our group and that we will be using for the lab. Now, we'll return to the story that started the other time, which was about what can I actually achieve, assuming that I have a superscalar processor with all the bells and jingles at the maximum level. And we started looking at branch predictions. Actually, what we started with this. Then no limits. Only the sky is the limit, which means that if only the sky is the limit, this is the number of instructions per cycle that I can get for some applications. And what I see is that they are different for floating point and integers, and they also depend on the program. Now, we have the clear tendency to split the data path of the processor in floating point and in integer, because those formats are treated in a different way. while an addition in integer takes one cycle, a floating point addition may take a lot more cycles. If you will take computer arithmetic, I'll explain you why when the time will come. If you don't take computer arithmetic, just trust my word, okay? Now, this is the limit, but now the question is, what can I achieve in practice? And in practice, I can achieve different things depending on the restrictions that I am placing. Then, in here, what we have is a relation between the branch prediction type and the instruction window, and also on the issue width. Then the instruction window is a pool of instructions where I'm looking for potential candidates for execution. In the ideal processor, it has no limit. I'll have as many as I can put there. In this case, I just have 2 kilo instructions in the instruction window. And I cannot issue more than 64 instructions. Those are now hardware limitations. Issuing 64 instructions is not as simple as it's said. Issuing 1, it's easy. Issuing 2 might be okay. 4, 8, still doable. When I think about 64, there are a lot of things which are complicating the story, but it's potentially okay. But now let us see what is the difference between infinity and restriction. And we see that the perfect prediction is doing quite okay, even though I'm restricting some resources. But nobody's perfect in practice, right? Maybe you are, I'm not. Then, depending now on what kind of prediction I'm doing, I may get closer to the perfect prediction. And what you see is that for floating point, things are looking better than for integers. The question is why? Now, I know you don't like me to ask questions, but you have to help me. You know, I see a diagram. It's beautiful, it has colors, but I have to understand something of that. And if I'm not relating those beautiful bars with some phenomena, I'm not learning anything. Why do you think prediction, normal prediction, can get closer to the perfect prediction for floating point, but is not that effective for integers? Just try. No hypothesis or no answer is wrong answer. Yes?
The floating points takes more cycles,
Okay.
and you have more time to figure out if the
Then, in other words, in floating points, first of all, I have longer execution of instructions, and I can hide the branch prediction. And also, if I look at the execution time of the program, there is no such a ratio between instructions, normal instructions, and branches as it is in integers. Here I'm computing fast, and your observation is correct. That kind of things you should try to do also in the reading assignment. You know, the authors are saying something. If you take it directly, it's not good. Then when you see such a diagram, and in general, you have to try to understand. Understanding is the key. Memorizing, to me, has no value. Okay? I mean, there are books. Okay. Come on. This is always going in the wrong direction. Now we look on a different angle. In order to do dynamic scheduling, I have to do renaming. Our friend Tomasulo taught us how to do that. Today in modern processors it's not done exactly like that, but the principle is the same. What I have now is I have again a kind of more normal processor with some assumptions, and I'm changing now the number of registers in the renaming buffer, which plus or minus we may think as the number of reservation stations. If I look at the ideal case, and I look at the other cases with limited things, I see that in the integers, the fact that I have now, how many, I don't know, 256 registers instead of the infinite number, it's okay. Then I can say that around probably 128 it's also okay. Which can tell me how many registers to put in the renaming facility in order to have a good performance. The fact that I'm changing from 100 or 200 to infinity is not really giving me anything back. The situation is not exactly like that in the floating point part. Now the question again is why? Why do you think the situation is not like that? Yes? There are two. You are closer. You know, the closer you are, the...
Maybe because the floating point operations are more dependent on each other?
Yes, I had more. Yes, it's a good observation. You?
Yeah, well,
The same.
Due to pipelining.
I have pipeline in both of them, right?
Yeah, but floating points operation take longer, so there's more pipeline.
Yeah, but I have to have things to fill the pipeline, which means they can be executed kind of in parallel. Then in the instruction, in the integer programs, there are more branches, okay? The instruction are, you know, in my possible execution window, I don't have that many instructions which I can potentially execute in parallel. Then the pressure on getting more and more registers for renaming is lower. While in floating point, due to the nature of the calculations that I'm doing, because floating point, what is doing addition, multiplication, division, okay? And rarely some branches, but those are, you know, due to the way the program is working. And because of that, in floating point, I have more pressure and I could use more registers. Okay, now, in this way, I can go further and make some other analysis. I can also look at the memory, you know, the licensing of the memory accesses. And in here, I have the same kind of story, you know, I'm trying to do this and I see different things for memory. And now you probably heard about Fortran. That's like a dinosaur of programming, okay? But people are still using it. If you want to do calculations, Fortran is still the best choice. It used to be a very, you know, ugly programming environment, but Fortran today is getting more and more structured. And what you see that because of the fact that in Fortran you have no heap, when you have some kind of, you know, the assumption that the global state is perfect, you have the same kind of performance as when you have the aliasing perfect. Now, in a nutshell, the more resources you are, the better you do, but there is a saturation point beyond which it makes no sense to put resources. Now, if I want to dimension a processor, that kind of analysis I have to carry on. And if I'm not mistaken, what you will have to do for your first assignment in the lab is to do something like that. Then we'll give you a platform, an application, and you will have to tune the platform to the requirements of the application. More details I cannot give you now because we are working on them. This is pipelining, by the way, right? We are one stage ahead, maybe 2 stages, hopefully. But if we flush the pipeline, then we all have a problem. No, I think we'll not flush the pipeline. Now, then, theory is one story, practice is another story, and these are things which you can kind of realize. You can realize with 64 instruction per cycle issue. You have to imagine that this is a big machine. There are a lot of complications there, burn power for that, but you can also get advantages. But the advantages you get only if the application provides you the potential instruction level parallelism to use it. Okay? Okay, now let's see what we have next. Okay, what we have next is now when we consider a realizable processor and we look on the impact of the window size. Then the window size, it's very important. If I want to issue 64 instructions each cycle, I have to be able to find them somewhere. My instructions are in the program, in the memory. I have to bring them close to the processor, to the decoding part of the processor, and I have to store them in a buffer. If my buffer is too small, I will not have instructions to issue. Then this is very important to be well balanced with the issue width. And you see here that, you know, the bigger the instruction window, the better the performance is. And it's going incremental, it's kind of linear. Per application, you know, the inclination of the line may change, but for all of them, I see a linear kind of behavior. And I also see that for the integer guys, whenever I go to 256, I'm in a kind of saturation. This may not be true for other benchmarks. And for floating point, I never get, you know, probably if I go to 500 or to 1000, I'll get to the saturation. It's a beautiful, very old-fashioned table. I love it. You know, those are processors from the past. What you can see here is you can see how the technology was evolving. Okay? Then we can look on the integrating IC process. And we started with 0.18 microns, which is today prehistorical technology, and things are going, you know, better and better. And there is a combination of better technology from the fabrication technology point of view and better technology from the architecture point of view. They are both pushing things. Now, I will not comment on all of those. What I will comment on is, yeah, that's another beautiful. Love those. You know, they look good, but it's the same as the beautiful diagram with bars. We have to get the essentials out of this table. And if I want to get the essentials, I would look, for example, at the evolution of the frequency. And you see that there is a kind of increase in the frequency, and then eventually the frequency is not giving, it's not paying back. And here we see what is the red one. I knew it was something wrong. Then you see here that I'm increasing the frequency, but here I'm decreasing the frequency. Performance-wise, by this increase, I get this improvement of performance. Now, I'm decreasing the frequency from 1.5 megahertz and I'm going to 400 megahertz and I'm doing better. Why am I doing better? Because I compute in a different way. A good processor will have a good balance between technology and architectural features and applications which are targeted. The tendency today is not to go for higher frequency. When you were kids, which was a long time ago, the technology was actually pushing the frequency to go higher and higher and higher. Eventually, this phenomenon stopped for a couple of reasons. Now, depends who you ask, the answer might be different. One of the issues is coming from the technology, and it's called variability. The smaller the devices are, the larger the influence of the probabilistic things in the fabrication on the performance of devices. I'm not sure if I told you that. Today, in transistors, the oxide under the gate of the most transistors, it's around 5 atomic layers. Think about 5 atomic layers. You all know how a MOS transistor looks, right? Okay. Now, if in the fabrication, instead of 5, I have 4, which is 1 less, right? I have 20% variation. And now, if I'm trying to increase the frequency, and my devices are exposed to that much variation, I have to take a big safety margin in the way I'm computing the clock cycle. Remember, we said that I'm splitting the logic in parts. I'm taking the delay of the longest stage in the pipeline. I'm adding hold and setup time for the registers. And I'm adding some safety margin for variations, because my logic in here may expand and shrink, not from the physical point of view, but from the time point of view, depending on what I'm executing. But this is true for all kinds of designs. But now I have the extra variation due to these technology things, which means, assuming that I'm moving from technology node A to technology node B, which actually should double the frequency, in the calculation, I have to take a safety margin which may get close to 100%. Then instead of running at the frequency of the new technology, which is twice as fast as the old technology, I will go with the new technology, but at the same frequency, or about that much, in order to compensate for those. The other story is the clock. Power. The higher the frequency, the more power you burn in the clock distribution network. Then power and variability actually changed the view of Intel, for example, which were pushing and pushing for higher frequency. And they eventually, turned towards multi-core. In a nutshell, this is the reasoning behind that decision. Things in practice, are a bit more complicated, but one of the fundamental things which is important for you in your future life is to try to extract the essentials from the practice. Okay? Then details may pollute your view on the things, and they may disturb your thinking. Okay? Now, with this beautiful table, you get a break.